Good evening, students. In this video, we'll be seeing about questions related to the writing part number 2. So those are the learning outcomes given. You can see that it focuses on electric potential to calculate and also potential energy, and also apply energy principles to calculate the work done by electric forces. So the sample questions that they have asked you to go through or revise is all the 3 questions from the textbook and also the question from PDF file. So in this we'll be seeing all these questions in detail, how to solve them. So that's example 3.4. So, yeah, and so you have all those questions. We'll discuss one by one, right? So before starting, what should you remember? The formulas for each one of them, and try to identify, which I keep telling my students, you might get confused when they ask electric potential and electric potential energy, because they have very similar pronunciation or wordings, so you may get confused. So always learn with the right symbol or alphabet so that you will choose the right formula from the formula sheet. So electric potential is represented by the letter V. It's capital V, and its unit will be in the SI unit will be volt, joules, or joules per coulomb. So you can use either one of them. And then electric potential energy is denoted by the letter U. So don't get confused with the two and swap the formulas, right? So energy is U. So remember, potential energy we always refer with U, and this unit will be joules. Alright, so electric potential is V, electric potential energy is U, and what are the formulas that you will be using for a point charge? So for E it is KQ over R. I'm sorry, for V you can see even I, okay, KQ over, sorry about that, KQ over R. And for potential energy U, it is K Q1 Q2 over R. Right, so we'll be using these formulas here. So these are all point charges we are discussing with, and you also might be familiar with the uniform field formula as well. V is equal to E times electric field times D if the electric field is uniform. The usual formula you would have learned it, or it is E is equal to V over D as well, right? We have discussed that when we were discussing electric flux. All right, so remember these while we are solving these questions. Now to the first question, which is example 3.4. You have 3 charges placed at three corners of a rectangle, and then you are asked to find the electric potential at a point P, and the distances are given in terms of the coordinates 0a, and then 0 and b 0, etc., where a is 8 and b is 6. So this shouldn't be confusing to you. If they give you in terms of coordinates, we know that if it's 0a, so x is 0 and y is a. So you can see that the point is Q1 is at vertically at a distance of A, and for Q2 it's at horizontally at a distance of B. So don't swap these order, because this is x is B and y is A, right? So this is x and this is y. So on the x-axis you have B, and on the y-axis it's A, and A is given as 8 meters. So this is 8 meters and B is 6 meters. And another common mistake that I see students make is that in the substitution, don't be in a hurry. Look at the distances. Q1 from the point P, they tend to use the value of 8 or swap the order. So better initially just write the opposite sides are equal. So label it on the diagram so that you don't make mistakes in the substitution. Alright. Okay, so these are the distances given, and you have the values of the charges given as 1.5, 2.5 and negative 3.5 in the question. Now let's solve this. This is a simple question. There shouldn't be much of confusion or difficulty in solving. This is just direct substitution of the formula. So V is equal to, we know the formula, so there are three charges, so at the point P, and since it's a scalar quantity, you don't have to worry about the direction, but keep in mind the sign or the type of charge each one of them are. Okay, here we have two positive charges and one negative, so you have to keep it in mind about the sign. So K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. Now every step is important. The reason is that so when you're rechecking your answers, even you can just spot any mistakes. So don't skip any step thinking it's not necessary. Sometimes you will get marks for those steps as well. Alright, so here we see the common term as K, and I would prefer to do one more step so that you save time while you're feeding the numbers in the calculator. So when you take the K outside, you get Q1 over R1 plus Q2 over R2 R2 plus Q3 over R3. Now do we have the values for each one of them? We do have Q1, which is R1 is the distance from P. This is what I said, you should not swap the distances. So let me label it on the diagram for you. So Q1 is the distance of R1 from P. Okay, and Q2 is this distance, so we need to diagonally take the distance from P, so this is R2, and Q3 is this distance, which is R3 here. Okay, again labeling the diagram will be beneficial so that you don't avoid careless mistakes. Okay, so we have R1 as 6, R3 as 8, but R2 is not given in the question. So you can find R2 by using Pythagoras theorem, which is, it forms the hypotenuse of a right angle triangle. So it's a right angle triangle, so which is square root of 8 square plus 6 square, right? It will give you 10 meters. So R2 equals 10. So now we have all the values of the quantities in the formula, so you can directly substitute and get the answer. So Q1 is 1.5 times, so it's microcoulomb. You all know the conversion, 10 to the power of negative 6 over R1 is 6 plus Q2 is 2.5 times 10 to the power of negative 6 over R2 is 10 meters we have found, plus Q3 is negative 3.5 times 10 to the power of negative 6 over R3 is 8 meters. So all this you will have to feed in your calculator and get the right answer. So when you calculate, you should be getting 562 volts. So that's example 3.4 that's mentioned in the Heikel. Now, so here remember, V is electric potential and the unit we have used is volt. Now second question, it's from the practice question, so end of chapter question 3.43. This is the picture given to you, so you can pause it and take a minute or two to read and understand what is asked, because you may get similar or a bit different type of question, but keep it in mind your aim is the same, to find the distances and apply it in the formula. So most of the times one or two of the distances might be missing, so you'll have to use your math skill, trigonometry, and then figure it out. Okay, I hope you have read the question. So here 4-point charges are placed in a square, so it's a square, so all sides are equal, right? All sides are equal, but side length is given as 2 times A. There is a reason they have given it like that. Alright, so A is 2.7 centimeter. So half the distance of the square, that's a midpoint, half distance is 2.7 centimeter. Okay, and all the charges have the same value, which is magnitude, that's 1.5, but you can see one type is negative, so other three are positive. Okay, now they ask you what's the electric potential generated by these 4-point charges at P. So three-dimensionally, if you look at it, it's exactly in the middle of the square, but not on the 2D plane, but above it. So it's like a three-dimensional position right above it. Okay, earlier we saw this is a two-dimensional question, but here you'll have to visualize it, then you will be able to figure out which distance had to be calculated for finding the electric potential due to all these charges. Right? So this is a question. Actually, I have placed another a diagram here for you to better understand. So this is a three-dimensional uh, version. So you have the point P right above the square. All right. It might look complicated, and as I always say, if you break it down into small steps, it will become easy for you. Okay. So what is the value that they have given? What do we know here? This distance is given as A. All right. And they've given you the vertical distance is 0, 0. This is X, Y, Z. So Z is like this point. So X and Y they've given it here. Vertically above it, this distance, this vertical height is C. Okay. And we need to find out R because this point P is at a distance of R from Q. And since it's a square, if you find one of the side, all the other four charges at the same distance from Q, which is, this is also R, that is this point, this entire distance. Here also will be R because it's a square. And even the other charge, the negative Q, is also at a distance of R from P. Alright, so our focus or first aim is to find R because we know the values of Q. The unknown is the distance of each of the charge from P. So I repeat, that's your question. You have a P right above a square which is positioned at a vertical distance of C from the point, and we do not have the value of the point P from each of the charge. Alright. If the P was in the middle, then you can find the two-dimensional distance. But since P is above, you need to find this distance from Q1 and Q2, Q3 and Q4. I hope you got it. Okay, now the values which we already have, we can use that to find this distance. Now if you look at, so always look for right angle triangle if you have, so that you can find the third side by using hypotenuse or Pythagoras theorem. Now this distance is A in the picture, right? And here this is also A. So if we can find the diagonal of this square, this is also a square, not the full square I'm talking about, the smaller, the one of the four sections square. So here you will have this distance would be square root of A square plus A square. Right? And this vertical distance is C. So if I redraw this on the side, so we have P at a distance here. This vertical distance is C. And this distance is square root of A square plus A square. And you will find this to be R. And notice this might look like it's not 90 degrees. Actually this angle is 90 degrees. Since it's three dimension, it's like coming out of the board. So this is also 90 degrees. So once again you can apply the Pythagoras rule to find R. So R will be square root of A square plus A square, this square, plus C square. Which is, so the square and square root could get cancelled. So square root of 2A square plus C square will be your R. Okay, so you can substitute the value 2 times 2.7 square plus C value is given as C value is 1 point, let us check here, 4.1 square. So you'll get the value of R to be 5.6 centimeters, or this will be equal to 0.056 meters. So this part is the confusing part, or something that you have to think and apply. So the vertical distance we need, it's given as C, and we were finding out the third side by using again Pythagoras theorem. Here on the bottom we had again a square, so if you split the square you will get this right angle is also, or if you draw a square, if you split it you will get a right angle. So that right angle is placed here. So this angle is also 90 degrees. So this side is A, this side is A. So the third side will be square root of A square plus A square. I hope that's clear. So we have found the first part of the question is done. So what's the question? They ask you to find electric potential. So electric potential, there are 4 charges. So you can expand the formula by writing the 4 formulas for the charges. So V is equal to K Q1 over R1 plus KQ2 over R2 plus KQ3 over R3 plus KQ4 over R4. Now, as I suggested before, you can take the K outside, and all these charges are the same, so I'll just replace it with Q itself. So, but 3 charges are positive and 1 charge is negative, so you have to keep that in mind. And the distances are same, so it is Q over R plus Q over R plus Q over R, and then minus Q over R you will have, right? So plus Q minus Q will get cancelled, and this becomes 2Q over R. So you will have 2KQ over R. So the formula becomes 2KQ over R. So we substitute the values. 2 times 9 times 10 to the power of 9 times the value of Q is given as 1.5 nanocoulombs. So 1.5 times 10 to the power of negative 9 over R is, we calculated it to be 0.056 meters. So all of them are in standard units. So you get the final answer, you get that calculation to be equal to, it should be 482. So you should get 482 volt. So that's the answer for 3.43 question. Now the next one, 3.6. So it's not related to electric potential, it is related to the energy or work done. So it's the second formula that we will be using it here. And let's see what's the question all about. 3 charges Q1, Q2, Q3 are located at the corners of an equilateral triangle. So equilateral triangle, we all know the sides will be equal. So if you take this as R, so all the sides are equal to be the same. And they have given you the length as 1.2. So the length is 1.2 meters. This is also 1.2. And this distance is also 1.2 meters. So hopefully the question will be easy for you, because there isn't any math skill or trigonometric ratios to be used to calculate. They've given you the distance directly. So now this is broken down into A, B, C, D parts. For each one of them you'll have to calculate to bring or to place a charge in a field. Okay, first let's understand how do we calculate, or what is the energy stored, potential energy stored in these particles. Is that when we do work against, or when you bring a particle from infinity into a field, so where you have, it's under the influence of the field, so you have the field directions. So to bring a particle into the field, how much work you are doing, so that will be stored in it as potential energy, and the formula to calculate is K Q1 Q2 over R. So R will be, so when you bring, if the charge is at this point, you have brought it from infinity to this point, so this is the place or the position of the charge. So say Q1 is here, so the distance between the two charges is R, and you get, so Q1, if you label this as say capital Q, so K Q1 Q over R will be the energy stored in this charge in bringing the Q1 into its field. Alright, so that's about the basics. You need to keep it in mind to apply the formula in such situations. Alright, so let's see what is part A asking us. Part A is to find the work done to bring the first particle Q1 to P from infinity. So this point P, when you bring from infinity, so you have to be careful so you don't have Q and R. So they are not placed in it already. If the charges are placed, then the energy is totally different. Alright? So when you bring the charge P, if there isn't any other field around it or any other charge around it, so there is zero work done because there is no particle to interact with. So for part A, Q1 to bring it from infinity, the work done, or if you take that as energy 1, is 0 joules. Remember, there should not be any other charges that is around it, right? So let's label these charges as this particle P as Q1 since we are familiar with the charge. So let that be Q1. Now to bring the second particle Q2, which is 2 picocoulomb, which is the conversion is 10 to the power of negative 12, right? Q from infinity. So let's say this is your Q2 charge. So P is already there, and then you're bringing the second charge, that is Q2, at point Q. Okay, so Q1 is here, Q2 is brought to this point. So how do we calculate the work done? As before, you need to have the distance R, and then it will be, so if you take the energy as U2 or U12, whichever is convenient for you, the energy between U12 will be equal to K Q1 Q2 over R. Right? So you can substitute the values. So all the values are given to you, so you don't have to think much. 9 times 10 to the power of 9 times 1 times 10 to the power of negative 12 times 2 times 10 to the power of negative 12 over R is 1.2 meters. So it's already in meters, so you don't have to do any conversion. So you will get 1.5 times 10 to the power of negative 14 joules. So this is for part B. Alright, so that's the energy required or the work done in moving the particle or the charged particle Q2 at position Q. Okay, now the third one, part C, is asking to bring the last particle Q3, that is 3 picocoulomb, to R from infinity. Okay, so how do we do that? So you already have two charges here. So you have Q1, Q2, and you're bringing the third charge at point 3. So you will have to do work against both the charges. So you'll have to do work against Q1 and against Q2. So what would be the energy? U31 has to be calculated, and U32 also has to be calculated. So that'll be the energy to bring in Q3 into this position. So as I explained before, you have to do work against charge Q1 and against charge Q2. So if you substitute the values, K, Q3, Q1 over the distance between them, R31, plus K, Q2, Q3 over R23. Okay, since here both the distances R13 and R23 are same, which is equal to 1.2 itself, so you can replace that with 1.2. This is also 1.2, and if there are any common terms, as I told before, you can take it out so you can save time in plugging in the values into your calculator. It's your choice. You can follow the step or you can skip the step and directly substitute all the values in this equation and get the answer. Alright, so if you wish to take the common terms, you can take K outside. Even you find here Q3 is also common, you can take Q3 out. Even 1.2 is common, so all you have inside is Q1 plus Q2. So as I said, it's your choice to do this step. If not, directly substitute all the values into this equation and get the answer. You should be getting 6.7 times 10 to the power of negative 14 joules. If we substitute for Q3, Q1 and K. Okay. And then for part D, they ask you to calculate the total energy stored or the total potential energy stored in the final configuration. So remember, this is a case where each charge is brought into the position. You don't have any charge that's already in the position. So if they're already there, the solution will be different. Okay, don't get confused between all the three. So for here, the first one was 0. So you add all the values of the energies that you have calculated. U1. So to bring U2, how much work you did. For U3, how much work you did. So 0 plus 1.5 times 10 to the power of negative 14 plus 6.7 times 10 to the power of negative 14. And I'm sure you'll be using the calculators appropriately by having brackets, otherwise your answers may differ. So the final answer will be 8.2 times 10 to the power of negative 14 joules. Remember to write the units as well. Okay, and the last question that's mentioned here in your EOT, this is 14A-B-C from the document or the PDF that was shared. So let's discuss those questions that's related to the learning outcome mentioned. So here you can see A and B both carry a positive charge. What is the electric potential V at the point X on the x-axis? They've not given you any values here. They've not given what's L or what is the charge. So you are expected to derive a formula or combine it, all of them, and simplify it as much as you can. So let's see what is the electric potential V at the point X on the x-axis. So the point is here. The point is here, and the charges are placed at A and B. So what do we need? So if you take this as Q1 is placed at A and Q2 is placed at B. Okay, and both carry positive plus Q. Now what do we need for calculating electric potential? You need to have this distance. So if you take that as R1, let's take this distance from the point as R2. So we need to know R1 and R2. So what's R1 in terms of say their denotions that they have given? So this is X, right? So it's going to be a right angle triangle here. So the sides are given as L and X. So let's use the same letters. So R1 will be square root of L square plus X square, right? Similarly, R2 will be equal to, here also will be the same because you have the sides to be X and this side is L as well. So you have the same formula for both. So basically the distances of these two charges are the same from the point on this point, say P on the x-axis. Okay, now they ask you the total electric potential. So let's start with the formula. So V is equal to, since we have two charges, the formula expands to KQ1 over R1 plus KQ2 over R2. So which is, since it is just Q positive charge, we'll just replace it with Q, and the distance is square root of L square plus X square, plus again you repeat the same, all the values are the same in the second expression as well. So you have like two expressions. It's like X plus X will be 2X, so you can have the same expression written once with 2 as its coefficient. So that is the total electric potential. So if at all they had given you the values of L, X and Q, you can substitute and find out the value from this formula, or break it down into steps and solve it. So that's 14A question and the answer, solution. Now 14B, what's different? They give values. Earlier it was plus Q for each of the charges, but here one is plus Q, the other one is negative 2Q. But the distances are still the same, so we apply the same rule again. So V is equal to KQ, that is positive Q, over square root of x square plus L square, plus in the second q2 you should substitute negative 2q, right? So square root of x square plus L square. So you can take all the common terms outside. So q minus 2q will give you negative q. I hope that's clear. So all these are common, so I take this as common term outside. So q minus 2q you will get, which will be minus q, which is with k. So this together gives you minus q. So the k times negative q will give you negative kq over square root of x square plus L square. Notice the difference in these two derivations. Earlier, both charges had same q and q, so it became 2q kq. Here, one charge was positive q, the other charge was negative q. So when you add them, you end up with this answer. Okay. Now coming to 14c. Here you're expected, there are values given, so we'll use appropriate formula and then apply or substitute the values and get the answer. Now if you read it, find the work done by the electric field in bringing C, there's a C from infinity to x is equal to 0. Okay, so always please read the question very carefully. We might think, okay, x is here and take the point here. No, they say from infinity to x is equal to 0. So the point is here now. Okay, so your point P is at the origin. And the first charge is plus q, that is, I'll use another color. Okay, this is q1. If you take it as this is plus 2q, and q2 equals minus q. And if we don't need this distance, the distance of the first charge from P is L itself, the distance of second charge is L itself, and they've given the L value to be 0.2. So this is third charge that's brought into existing two charges already. Sorry. So if you take this one to be q3, so q1 is already there plus 2q, q2 is there, and you're bringing q3 into point P. So it has to do, q3 has to do work against q1, it has to do work against q2 as well. So that will be the total energy required to bring the point or the charge from infinity to P. I hope that's clear. So we'll expand the formula. K q3 q1 over R31 or 13 plus K q3 q2 over R32. Now notice this distance R3 and R2 are the same, which is L. So let's use those values and take the common ones outside. So q3 is common. So K q3 over, I can put as L because as I said, R31, this distance is L and this distance is L as well. So you can notice here this is L and this is L. So I've taken all the common terms outside. So what's left now? Q1 plus Q2. Okay. Now, and they give you the charges for each. Q stands for 12 nanocoulomb. Okay, remember that. And before that, again, there is a little step to do. Q1 is plus 2q and Q2 is negative q. So we will substitute all that. So K, this is q itself over L. Q1 is 2q. Q2 is minus q. So the formula even simplifies further. So 2q minus q is q itself over L, or it is kq square over L. Okay, so as I told you earlier, you can use the long step to substitute. It's fine, it's up to you, but kind of when you combine it and do it correctly, if you're very comfortable and confident, it will save you some time. Okay, 9 times 10 to the power of 9 times, you have the charge is given as 12 nanocoulomb, which is 12 times 10 to the power of minus 9 or negative 9 over L is 0.2. So taking all these values, you should be getting 6.48 times 10 to the power of negative 6 joules. So that's the total energy required to bring the third particle from infinity to this point. And notice, it's always the distance between point A to where you are bringing it in. So here the distance is L, but in the previous question they ask you what is the electric potential energy. This is different, electric potential. So even if they ask you what's the electric potential energy required to bring a charge from infinity to point X from the origin, then your formula will be what? KQ1 Q2 over the square root of this x square plus L square, because that's the distance between the two charges. I hope that's clear. All the best.